So this is group 5 and we are working on, group 20, and we are working on a contrastive physical self-supervised learning and knowledge installation for wine quality prediction. So, so, so in this video, we'll explore how to build a predictive model that can assess the quality of wine based on various features. So at first, we shall begin by understanding the data set we are using. So at this point, we are using the red wine quality data set that is from the UCI Machine Learning Repository. So the first thing we are going to do here is we shall import our libraries. Then after that, we shall do data processing, handling missing values, handling null values. Then next on that, we shall perform the exploratory data analysis. After there, we shall build on different machine learning modules. Then we shall evaluate their performance accuracy to come up with a conclusion of the final model. We shall deploy for predicting wine quality. So the first thing here is I import our library. So I run it. So here, so it is running. Taking a bit long. Have to be patient. So these are our different libraries we shall be using. Have the pandas, the NumPy, the sklearn. This one is for training the models. Then the sklearn is for that one for assembling various models. Here we see that our models have been successfully imported. Then the next thing is we have to load dataset we are going to use. And here I already told you we are using the red wine quality dataset from the UCI Machine Learning Repository. So here is our dataset. So back to our code, here it is. So we have to load this code to our working environment. So when I run it, see that our code has been loaded, and this is our red wine quality dataset have been 1,599 data points with the 12 physiochemical attributes that we are going to use. Then the next thing is we have to understand the kind of the data we are doing. So when I run this code, you see that these are the data points we have and the columns within it. Then here, it has outlined for us the column headers. So what are under these column headers? I have to describe this data frame, see what my column, those physiochemical attributes contain. So when I run this, should be able to see that each attribute has these 1,599 data points under it. And these are the ones we are going to put them into different categories that will help us to assess, like when we are given different attributes with different, let me say, range, then we assess it, we shall be able to tell that this one with these attributes and this range, it's under this quality. So then the next thing on that is to know the data type I'm working with. So when I run this, you see that my attributes here, they have a continuous data, like in a float form, but then my quality, which is my target value, is an integer because we are working on it. Like when we are scaling, we are going to give it from a range of 0 to 10. That's for our quality, in that the ones we shall get when it's greater than 7, those are the ones of good quality. Then less than 7, we shall term them as not bad, but like poor quality. So that's why I'm having it as an integer. Then the next thing on that, I have now to handle my data. Am I having missing values? Am I having null values? And how do I fix that? So the first thing is checking null values. When I run this, I'm able to see that my data is very fine. I don't have any null or missing value in it. So the next thing is I have to choose the unique quality, the unique quality range I'll be using instead of using from 0 to 1, which can be bulky. So when I run this, I get the array. So I'll be working with this sample array. So the first thing I'm going to do is to visualize this using a heat map. And when I run this, you can see these are my data points and my attributes, but then they are mixed up. But then how do I sort to differentiate between them? Let's get here. Here, I'll first separate the categorical values from those numerical values. And this is what I come up with. And my numerical values contains those column headers, which I'm going to be working with. Then the next thing on this is loading my data frame with their necessary data. So this is what I do at this point. And when I run that this is what I get. You see that at a quality range of maybe from 0 to 3, I have a count of, okay, sorry, but I have a summary here. Like at 3, I have a quality count of 10. You can see at 4, I have 53, and so on for all the unique values I'm working with. Then the next thing is code, sorry, it was a repetition. It still shows the counts of the unique quality range I've chosen to use. So the next thing is I have here an histogram showing like the correlation of the different attributes that we are working with. As you can see, for residual sugar, fixed acidity, volatile acidity, they have their correlation is spread differently. Then the next thing is I have estimated the relationship between quality and different properties. So for the first one is for quality in relation to density, and we see that as density increases, the quality of the wine also remains the same. Here I have with volatile acid. I think let me also show the one of pH. You see how quality reacts with pH in wine. So we see that as the pH increases, the quality of wine like gradually reduces. It reaches at a certain point, becomes constant, then begins reducing again. So the next thing here shows how my data is distributed generally. So when I run it, yeah, so this is it. You can see how the different attributes are distributed within a wine sample. So the next thing is checking for outliers. And these outliers, these are the data that can contradict with our original sample, the data that we described up. I think show the describe. So this was the data we described, and for this point, we are checking out for the possible data that may be available and contradict to it. So when I run my code, it should be able to visualize for me to see whether my attributes have some outliers or not. So yeah, it is. We can see that in fixed acidity, yes, our data set has some outliers, as you can see. And this one has more of it. At least here it is minimum. As you can see, the different attributes have different outliers. So let me welcome my colleague, take you through the next step on how to deal with those outliers. Yes, I as my colleague can say, and has talked about the outliers. Then the method that you use to work on those outliers for the IQR method, which is the interquartile range method, as you can see, this is the code for it. If you run it, you can see the data frame after removing outliers. You can see the different attributes that includes with sulfur dioxide, the total sulfur density, pH, and sulfates after removing the outliers. Then we come to visualizing data on a heat map after removing outliers. Here, you now create the heat map. When you run it, you can see how different features of our data set are reacting. Yeah, we have fixed acidity, volatile acidity. Then this side we have quality, alcohol, sulfates. So you can see how different features are reacting with the. Then here we import, we go to yeah, here you can see the total number of wines we have is 1,599. We have wines with rating 6 and above being 855. Then wines with rating less than 5 being 63. Then the percentage of wines with quality 6 and above being 53.47. Then we go to the target variable distribution. As you can see the code for it, when you run it, you can see the distribution of wine quality rating. It is the quality rating over the count. It is quality over the rating. Yes, you can see when quality is at around 3, the rating or the count is on around 10, 15 there. Then 4, around 70, like that. When you go to the splitting the feature of the target, you can see the code for it. Then when you run that code, you can see the output being fixed acidity, volatile acidity, with the different features of our data set. Then we go to the separate independent and target variables. Here, our target variables is, of course, the quality we are testing. Then for the independent variables are those ones that can come in as we are working with the code. As you can see, here we have the unique values, as my colleague explained to you. We have the 5 and the what and their corresponding data points. Balancing the target, you can see the code for which then when you run it, you can see that they are now matching. The 5 is matching. This 5 had, yeah, it is now matching. As you can. Then we go to the splitting the data set. We put pandas. You can see. And when we go to splitting the data set. As you can see, in the process of splitting, you have to first separate data into training and testing sets. Then you can select, like you can say 80% of it for the training. Then the rest is the one for testing. You can see the number of training data points. We have 1,279, and the number of testing data points is 320. Then we go to the training multiple models. Here we initially the models, initializing models for comparison. You can see the different algorithms with the way they relate. We have logistic, diffusion, random forest. Then you go to train and evaluate each model. Like here, you have the model name, model, like as you can see the code. Yeah, the models we've already talked about. So let me continue again from that point. So after training our different models, we have the logistic, the decision trees, the random forest. We also went ahead, evaluate like their performance and see which one has the highest accuracy, which one has the lowest or medium accuracy. So when I run that model training and the evaluation code, it comes out that the random forest model had the highest accuracy, and that one will be taken as our training model. So here, if I run these two, shall be able to see how different performance has been grouped to see that precision, the recall, the F1 score, and the support. This is what they use to evaluate which model had the highest accuracy, low, medium, and that after visualizing the accuracy classification, we came in here and compared the results. Then after comparing the results, as you can see, this is our comparison prediction model. So we see that the random forest has the highest accuracy of 0.7, and the one with the lowest accuracy, 0.5. You also see that the decision and neural network tends to have the same accuracy. So from that point, we selected our best model, which is the random forest with an accuracy of 0.7375 because we specified it to 4 decimal places. So after selecting our best model and